This is the Discovery Files podcast from the U.S. National Science Foundation. High in the Andes Mountains of Chile sits the NSF-DOE Vera C Rubin Observatory, jointly funded by the U.S. National Science Foundation and the U.S. Department of Energy Office of Science. The observatory is a brand new astronomy and astrophysics facility with cutting-edge technologies, including the LSST camera. It is the largest digital camera ever built and will take detailed images of the southern hemisphere sky for the next decade, covering the entire sky every few nights and creating an ultra-wide, ultra-high-definition time-lapse record, the largest astronomical movie of all time. The data collected at the observatory will allow researchers a better understanding of our universe and reveal answers to questions we have yet to imagine. The telescope's namesake, Dr. Vera C. Rubin, was an American astronomer born in Philadelphia in 1928. She earned her bachelor's degree in astronomy at Vassar in 1948, her master's degree from Cornell in 1951, and her PhD from Georgetown University in 1954. Beginning in the early 1960s, Dr. Rubin studied motion in space. Her work provided convincing evidence for the existence of unseen dark matter in the universe. Prior to her work, dark matter was a concept that had been introduced, but not taken seriously. Since then, scientists have figured out that dark matter makes up more than 80% of all the matter in the universe. Scientists have spent the past decades on a quest to figure out what dark matter is and what role it plays in sculpting the structure of the universe. Physicists try to identify its nature using labs here on Earth, while astronomers continue to make observations of dark matter's gravitational influence on other objects in space. Essentially, Vera Rubin's work created a whole new subfield of astrophysics around a brand new idea. We now present some of Dr. Rubin's thoughts on the universe in excerpts from her lecture entitled What's the Matter in the Universe?, recorded in November of 1994.
We live in a universe which is amazingly beautiful, enormously large, incredibly complex, and one of the remarkable features, I think, is that at least some of it can be understood. 60 years ago, Hubble, Shapley, and others understood that we live in a galaxy, that space is expanding, carrying the galaxies with it, and they understood this in terms of what they called the perfect cosmological principle. Everywhere, in all directions, space was homogeneous, isotropic, and smooth. For the last 20 years or so, we have understood that at least the universe which we observe with our optical telescopes, radio telescopes at all wavelengths, the universe is very lumpy, that stars form into galaxies, galaxies clump into groups, into clusters, clusters form into superclusters. And over large regions of space, the added gravity of these large conglomeration means that large streams of galaxies are moving toward regions of higher density. Another thing we've learned is that most of the universe is not radiating. It's not radiating any wavelength that we can see with our telescopes, undetectable with all the instruments that we have so far been able to build. We're really seeing only perhaps 10% of the universe. I think there are really very major features of the universe that we have not yet detected. All the observational evidence we see is consistent with a low-density universe that will expand forever. Even counting the dark matter, which we can detect by its gravitational attraction, we cannot count enough matter to halt the expansion of the universe.
In the next section, Dr. Rubin explained how stars arrange into galaxies.
I presume all of you know that if you go outside on a very clear night, all of the stars you see are members of our own galaxy. That means they're gravitationally bound. They're all orbiting in mostly circular orbits about a very distant center. At the position of the sun, it takes us about 200 million years to go once around the galaxy. So we've been around 10 or 20 times in the age of our galaxy. The stars are not distributed at random, but they're flattened to a plane. so that when we look through the plane, we see vast numbers of stars along the line of sight, and we see these in a bright band that we call the Milky Way. It was a puzzle to the ancients what the Milky Way was. It was not until Galileo built his telescope in 1609 and pointed at the Milky Way could he say that the Milky Way was composed of lots of stars. As you see it from Chile, the Milky Way goes overhead. We can't see all the way to the center because the Milky Way is composed of more than just stars. There's gas and dust, very low density, but long enough path length so that it brightens, but we're not looking totally toward the center. Seen head on, we think our galaxy would look like this. A central bulge. Even in the disk, the stars are not arranged at random, but tend to clump in these long stringy arms, which we call spiral arms. The brightest features are not individual stars, but clusters in which generally new stars are being born. Stars are born from the gas and the dust. They evolve and they die. We are located somewhere on an outer arm. As I said, it takes us 200 million years. Some stars are born and evolve and die before 200 million years has gone by, and so they don't even make one revolution. The arms, they're not a fixed pattern. The orbit of individual stars carries them into the arm, where they spend, due to the extra gravity, due to the higher mass, spend more time there, move out, and continue their orbit. The arms are really the locus of points of regions of higher density, much like a traffic jam on a highway. If you looked from an airplane view down in a region where there was a bridge or a bottleneck, you would almost always see cars there, but they would be different cars at the same time. An important feature of galaxies is that stars are very, very far apart. Relative to their diameters, you could put about 1% of all the stars. You could put 1 billion stars in our galaxy between the average separation of 2. And that means the stars don't gravitationally interfere. In contrast to stars in a galaxy, which are very far apart, galaxies, relative to their diameters, are very close together. Virtually no galaxy is isolated. We have these 2 small satellite galaxies visible to the naked eye in the southern hemisphere. They are gravitationally bound to our galaxy. They orbit in paths that take these stellar systems through the disk of our galaxy. And when the gas in these systems meets the gas in our disk, there are shocks, there are gravitational tidal disruptions. These small galaxies will soon cease to exist. Successive passes through our galaxy will force them to lose energy, and they will ultimately become part of our galaxy. And we now understand that this merger process is a very active driving force in the evolution of galaxies. The galaxies I've been talking about have been principally spiral galaxies, disk galaxies. When we look at clusters of galaxies, especially centers of clusters, we see that most of the galaxies are spheroidal, relatively featureless, and we now understand these as the end products of the merger of 2 disk galaxies. Clusters are important for several other reasons. It was in the early 1930s that Fritz Zwicky first suggested that there must exist in clusters much matter that was dark. He called it missing matter. He recognized, as soon as he had velocities of the individual galaxies, that the galaxies were individually moving so rapidly that the cluster should disband. But it was not disbanding, and therefore he concluded that there had to be more matter in the cluster than you could see, and that matter was in fact holding the cluster together. The gravity is sufficient to have halted the expansion of the universe. So centers of clusters of galaxies are not expanding. We are expanding from the Virgo cluster, but we're expanding slower than if the cluster were not there. Astronomers often carelessly say we're falling to Virgo, but that's not so. We are expanding, but slowly. If the universe lives long enough, our expansion from Virgo may ultimately be halted, and we might then truly start to fall in. Astronomers can point to the region around the cluster in which new galaxies are at present starting to fall in. We're living in an era when clusters of galaxies are forming.
Dr. Rubin next explained how you might measure how much matter is to be found in the universe.
And I'd now like to turn to the discussion of how you learn how much matter is involved in all of this, especially if some of it is dark. And the answer starts with Newton. What Newton understood when the apple hit him on the head was not that apples fall, because everybody knew that apples fall to the ground, but what he understood was it was the same force of gravity that pulled the apple to the ground, that pulled the Earth around the sun, pulled the moon around the Earth, and we would now say pulls the sun around the center of the galaxy. The forward motion of the Earth around the sun is so great that although we are continually falling to the sun, we can't hit it, because our forward motion carries us in the forward direction and the sun is curling under us, if you like. So if you know the distances and the velocities, you can calculate how much matter there is in the sun. And so you are using each of the planets as a test particle in the gravitational field of the sun. What Galileo knew when he dropped the feather and the lump of coal or something from the Tower of Pisa was that it doesn't matter what the test particle is. It doesn't matter whether this is a planet here or a bit of dust or an elephant or another sun. If you just have something whose velocity and distance you can measure, you can interpret from that how much matter there is interior to that position. And this is what we do when we attempt to determine how much matter there is in a galaxy.
After she explained how Isaac Newton and Galileo's work was still relevant to measuring matter, Dr. Rubin moved on to how observations she and her colleagues made provided evidence for the existence of dark matter.
So some years ago, with my colleague Kent Ford, who is here tonight, we embarked on a long-range program to measure the motions of stars in galaxies. Much of the work was done at Kitt Peak. Kitt Peak is also run by a consortium of universities funded by the National Science Foundation. So what Kent and I did was pick some galaxies that were moderately inclined. Stars are orbiting in the sense that the arms are trailing. So we use this instrument called a spectrograph with a grating which disperses the light into its constituent frequencies, like a rainbow. And we use a long slit so that each point on the galaxy, we just make a skinny cut across the center, reproduces in the spectrum this line of hydrogen alpha. And by measuring the location of each one of these knots on the spectrum, we can determine how rapidly each point in the galaxy is moving. So even though we go observing on nights that we call dark, the radiation from the night sky is displaced this much from the night sky. So that's the evidence that the universe is expanding. This galaxy is moving away from us, and its hydrogen alpha line is displaced toward the red. But you can see on one side, the galaxy velocities are lower with respect to the center, high on the other. This is due to the rotation of the stars, and that's what we're attempting to measure. And what you see, and what was unexpected, is that the velocities, as far out as we can measure, do not in fact fall. The light from this galaxy would predict that the rotation velocity should have gone up, turned over, and then fallen way down. And the fact that they didn't, we interpret it as meaning that there is more matter in the galaxy that we can see, and the velocities of these stars are remaining high in response to the gravitational attraction of this matter that we don't see. The question, does it exist, is generally answered affirmatively. The only way we could explain the observations without dark matter is to say that Newton's laws do not hold over distances this large. And the scientific community is really reluctant to say that Newton's laws don't hold, although there are very capable scientists attempting to make relativistic cosmologies which are altered, and if they are successful, we may have to reconsider. But ignoring Newton's laws, then we have evidence that it exists. Newton's laws, for those of you that remember your high school physics, tell you that the mass interior to any r can be calculated if you just know the distance r and the velocity squared. So if for any test particle at distance r from the center of a mass m, the mass can be calculated with a constant. We have a rotation curve. The light in the galaxy would predict that, and so this is the contribution to the velocity from the dark matter. And therefore, if you want to study the dark matter, you want to go to the largest radius that you can possibly get. And the other comment I wanted to remember to make was that clearly the contribution to the dark matter gets more important as you go to larger and larger distances.
We close our visit with Dr. Rubin's 1994 What's the Matter in the Universe lecture by hearing how measuring matter lets astronomers and cosmologists answer questions about the universe.
And the question that cosmologists would like to answer, and I think most people would like to answer, is, do we live in a universe that will expand forever? Or will the gravitational attraction of all the matter inside of the universe ultimately halt the expansion and start it recontracting? Or is it just exactly flat? Do we live in a universe in which the density is just the closure density so that it will sort of halt the expansion and just kind of sit there? And the evidence that's been gathered most recently, a lot of it from X-ray observations of clusters, is in fact that it does turn over. We can observe many of the very large clusters in X-rays, and it turns out that the dominant mass in the clusters is very hot gas, but they still have densities relative to the closure density that just sit around here. And it's based on that kind of evidence. The density in luminous galaxies falls off like this. Dark matter is more dominant than the galaxies. The X-ray gas becomes even more dominant as you go farther out. The total density implies a mass relative to its luminosity of about 100. And so we are left, I think, with evidence that clearly indicates that at the present time, there are no observations that imply that we live in a closed universe. Now, the problem is that based on the most accepted cosmologies, theorists would like the amount of matter in the universe to just match the closure density. So if we live in a universe which is closed, if the density of the universe is high enough to halt the expansion, then that matter must be unconventional. It must be unlike the matter we have so far detected in the universe. And that's the problem that cosmologists and particle physicists are attempting to see whether they can build particle detectors to detect non-baryonic matter that could be the constituent that closes the universe.
Dr. Rubin and her colleague at the Carnegie Institute of Washington, Kent Ford, studied more than 60 galaxies. The work resulting from these observations eventually convinced the science community that dark matter was real. Dr. Rubin passed away in 2016, but her legacy lives on. The NSF-DOE Vera C Rubin Observatory will provide a vast astronomical dataset for unprecedented discovery of the deep and dynamic universe. As the observatory embarks on its quest to capture the cosmos, we'll have to wait and see if dark matter is revealed once and for all. But there are sure to be countless discoveries in the years to come. What's the Matter in the Universe was the 29th annual Jansky Lecture from the National Radio Astronomy Observatory, recorded in November of 1994. For the Discovery Files, I'm Nate Podker. If you want to see the entire lecture, or watch video versions of other podcasts, head over to NSF's YouTube channel at NSF Science. Please subscribe wherever you get podcasts, and if you like our program, share with a friend, and consider leaving a review. Discover how the U.S. National Science Foundation is advancing research at nsf.gov.